Hi students, welcome to Year 9 Science and Unit 2, Our Amazing Earth. This is video number 8, and in this video we're going to focus on convection currents. Now what we need to do is we need to illustrate with a diagram that continental movement could be driven by convection currents within the Earth. In actual fact, we're going to have a look at two contrasting theories here, but we're going to focus on convection currents because convection currents is a really nice story to link with plate tectonics to together produce a mechanism which allows us to really nicely explain these phenomena that we've talked about, including continental drift and seafloor spreading. So what we need to do then is we need to marry our idea of plate tectonic theory with convection currents that are occurring in the mantle, certainly in the lower part of the mantle. Convection currents can be set up in fluids where the particles are capable of flow. They do this at a hot spot. And we've looked at convection in the context of our particle model and our kinetic theory. And so what that tells us is that particles that are heated are able to transform that heat energy into kinetic energy. And that means they will move faster. And at that point, they will move quickly away from the heat source, up, generally speaking, away from where that heat source is. What will happen then is they'll either continue to keep rising, perhaps produce some sort of volcanic activity on the surface, or the heated material may start to spread underneath that solid lithosphere. So we know the asthenosphere is the sort of plasticky molten material that sits underneath the solid lithosphere, and that the lithosphere itself has been separated into a series of different plates, and each of these plates is actually capable of moving relative to one another. So if we call this plate 1 and this one plate 2, then what we notice is that as the heated material is rising above the hot spot in the mantle, that the two plates that are not held together rigidly but are capable of flowing actually start to push apart from one another. So plate 1 is heading in an anti-clockwise direction according to this diagram, and plate 2 in a clockwise direction according to this diagram. So the two plates are actually moving apart from one another. This really nicely explains not only some of the continental drift that we've seen, but also the idea of seafloor spreading, which is new material, new crust that's being created at the center of where the hot spot is, and that is depositing new oceanic crust in between two plates, which are moving apart from one another. Now you can see as these convection cells, so this is a convection cell, and there's another one here and another one here, and you can see that we've got a series of these all throughout the mantle, and that plates are riding on these different convection cells. And we've drawn this in 2 dimensions, but obviously it's a sphere, it's a 3-dimensional thing, so these can be occurring side by side as well as sort of in a ring in the way that we've kind of represented it here. But what it also means is that there are other areas. If I call this plate 3 and on the other side I label plate 4, then you can see that while plates 1 and 2 are actually pushing apart from one another, plates 3 and 1 are coming together, and likewise plates 2 and 4 are coming together. So you can actually see that there are different sorts of things happening at these boundaries between the plates. Now these boundaries between the plates are also corresponding to boundaries between adjacent convection cells. This is a very, very important part of the story of plate tectonics, because the plates moving relative to one another is a good story that helps link ideas or observations like continental drift and like seafloor spreading, but it doesn't explain why the plates are moving from one place to another, or why they're moving in different directions, or why they're moving at different speeds. when we link the idea of plate tectonics to convection currents within the mantle, we can actually see how these plates might be moving relative to one another. Now, this is probably the best story, but it's not the only story. There is another. The other idea is this idea of slab pull, ridge, push. And when you analyze this, what you're looking at particularly is what happens at a phenomena known as a subduction zone. Now, we haven't talked much about this at the moment, but a subduction zone is basically a place where more dense material, like oceanic crust, goes underneath less dense material, like continental crust. And as a result of that, you get this sort of plunging down into the earth of the crustal material, and that creates a deep trench and a region that we've called a subduction zone. But in addition to that, what it does is it creates this kind of frictional force between the plate that's moving down into the earth and the one that's adjacent to it, that's kind of grinding against it. This is a phenomenon which is being described as slab pull. At subduction zones, gravity is actually pulling the denser plates down into the earth. So there's like a tug of war going on, dragging the plate down further into the earth. And obviously, as that's happening, that's going to be transmitted along the whole length of the plate. If behind that plate we also have a place where there's, for example, a mid-ocean ridge, so there is volcanic material that's actually being added to the crust at this point, what that could also be doing is pushing the new crust away from that source. So there is a push happening here and a pull happening here. This phenomenon is known as slab pull, ridge push, and it's another potential explanation for the mechanism of why the plates are moving. Now, it makes sense, and obviously the point with models is models are designed to explain phenomena. Our models are only as good as their ability to actually explain the observations that we see. Now, this does this, but for me, the idea of convection cells within the mantle, which are acting on plates independent of one another, moving some together, moving some apart, moving some side by side, fits slightly more nicely from my perspective. And it's one that we're going to be looking at as we continue to analyze what's actually happening at plate boundaries, but we'll save that for another video. Thanks for watching.